Hello and welcome to this new uh, chapter where we are going to see one very important application of channel capacity, and in particular we are going to talk about the capacity of Gaussian channels. So Gaussian channels are channels that closely model the physical layer of many communication systems where we send waveforms, for example, over a radio channel or over a cable. The system can be modeled as a linear system, so essentially as a filter with an impulse response. Our waveform will arrive to the receiver after attenuation, distortion due to the filtering, and at the end, the receiver will demodulate this waveform, and in the process of receiving it, amplifying the signal level and the sampling and converting from analog to digital, etc., it introduces some noise. So the noise can be interference when it comes from outside the receiver, or it can be just simply thermal noise when it comes from the electronic components inside the receiver. When this noise is modeled as Gaussian noise, we are in the presence of additive Gaussian noise, and therefore we talk about Gaussian channels. So, in order to handle Gaussian channels, we have to generalize a little bit or extend a little bit the theory we have seen so far to the case of continuous random variables, because Gaussian distribution, as everybody knows, is defined over the reals, and we say it's a Gaussian random variable is continuous in the sense that its CDF has no jumps. So it's differentiable and therefore has a density, probability density. So we are not going to talk about probability mass functions anymore, but we are going to talk about probability densities. And, the definition of entropy works for discrete random variables. Entropy for continuous random variable is essentially not very interesting and not defined. So we have to introduce another quantity, which is some people don't like it very much because it's not a real information measure. In fact, it can be negative, while entropy, we all know that is not negative. But nevertheless, it is useful in several results, and so we introduce it. This is called the differential entropy. So the differential entropy has formally the same definition of entropy, but it applies to continuous random variables, or more in general, continuous random vectors. So we have a random vector xn defined over the reals, so a real component, with a certain probability density that we call small p sub xn of x, and we define the differential entropy. We use the symbol small h to distinguish it from big H. Big H is the entropy. Differential entropy is simply, you see exactly the same definition, is minus expectation of logarithm of the probability density of the vector. So explicitly minus the expectation written as an integral, so it's the function that we are computing the expectation of, times the probability density function integrated over dx. Okay? So when you compare this definition with the definition of entropy for a discrete random vector, what are the differences? Formally, the definition is very similar. The joint entropy of a discrete random vector, as we know, is minus expectation of log. But here, instead of the probability density, we have the probability mass function, and written explicitly as we have a sum over all possible values of our random vector in the alphabet x of p sub xn of small x times log p sub xn of small x. So, okay, you may say, well, they are the same thing, right? For the definition is very similar, and all what you have to do is to replace, instead of a discrete sum, you replace as an integral, and the interpretation of probability density is that basically px dx is the infinitesimal probability mass associated to the point x. But when x is a continuous variable, yes, this makes sense, but you see when we take the logarithm here, there should be log of px dx, not just log of px. And log of px dx, well, when dx goes to 0, because it's an infinitesimal, then log becomes minus infinity. So we see that this definition does not extend. So we define this differential entropy in this way, and it turns out that the differential entropy retains several properties of the entropy, but is not an information measure. In fact, the main property it does not retain is that it is not necessarily non-negative, so it can become negative. However, as done for entropy, we will sometimes indicate h of px when we want to indicate that small h, the differential entropy, is a function of the probability density px, is not a function of the random variable x. And two immediate properties are the translation property. So the differential entropy is invariant by translation. If we take a random vector and we just add a constant vector a, well, the differential entropy of x plus a is the same as probability is the same as the differential entropy of x. And the other thing is the scaling. So if we apply a linear invertible transformation from Rn to Rn, so a matrix A n by n invertible operates a transformation between Rn and Rn, so it's like a scaling and rotation of a vector. The differential entropy of A times xn is equal to the differential entropy of xn plus the log of the determinant of the transformation. So those are two immediate properties. Just to give you an example, for example, for the uniform distribution, so what is the uniform distribution? It's a distribution whose density is uniform over an interval. For example, in this case, this example considers the interval 0, a, and the density is simply equal to 1 over a over this interval. So when you integrate a density over all possible values, you have to get 1, and the density, probability densities are non-negative functions. And if I apply the definition, this becomes the differential entropy of a uniform random variable x is the integral from 0 to a of 1 over a times log of 1 over 1 over a, which is log of a, so the result is log of a. If I generalize this to a random vector in a high dimensional space that is uniform over a certain volume of measure, so a certain area of, certain, compact set that is, or that is indicated as D as a domain of the random variable, a uniform random vector uniformly distributed over a certain domain like this is simply logarithm of the volume of the domain. An important case, which in fact motivates us to look at this continuous random variable, is the Gaussian distribution. So what is a Gaussian or normal distribution? We use this notation. X is normally distributed with mean mu and variance sigma square. It means that its probability density is this well-known Gaussian distribution. This is the well-known Gauss bell curve centered at mu, and sigma square determines the spread of this curve. Okay. In the case of multivariate Gaussian distribution, so when we consider jointly distributed, jointly Gaussian random vectors, and we use this symbol. So xn is a jointly Gaussian random vector with a mean vector mu and covariance matrix sigma. It means that the PDF, the joint PDF of the vector x is given by this expression is 1 over 2 pi to the n divided by 2. N is the dimension of the vector. Determinant of sigma to the 1/2, so square root of the determinant of sigma, and then exponential of minus 1/2. And then this is called a quadratic form, where every time we have a row vector, because this is transpose, times a matrix, times a column vector. So the dimension is 1 times n, n times n, n times 1. So this is a scalar, it's a 1 by 1 object, okay, that can also be written explicitly. And if I have a quadratic form of the form A transpose times a matrix n times A, this is simply the sum over all I and j of AI, AJ for all possible pairs times the element Mij of the matrix. Okay, you can check, recall your notion from linear algebra. If you're not familiar with the matrix vector multiplications, that's the time to review it, because it will be used pretty intensely in every single processing, communication, control courses. You have matrices and vectors, and including a little bit of information theory when we talk about signals, because at the end, what is a signal is just a vector of samples, and an operator, a linear operator, is a matrix. So we use vectors and matrices all the time in information theory and communication. Okay, so basically, okay, here is the structure of n-variate joint Gaussian distribution, and now we are interested in determining the differential entropy. So it's important to notice that when we take the logarithm of this Gaussian distribution, what we have is that, you just take the log of this thing. So you get a logarithm of a product becomes sum of logarithms. So we have one term that depends on this 2 pi raised to the n-half. We get this. Then we have this term that is the determinant. And then we have the quadratic form. Then when we take the expectation with respect to the variable x, well, all the constant remains the same. So minus the expectation, we have the minus the first term, minus the second term, and then we have the expectation of this term. So let me show you how to compute the expectation of this term once for all, because you have to learn it. This is something completely trivial, but you never know what is trivial for students and what is non-trivial. So I assume that you must be at least once shown something. So we want to compute the following thing, expectation of this quadratic form. So we have expectation of x n minus mu transpose sigma to the minus 1 x n minus mu. Okay, x n is a column vector, so when you transpose it becomes a row vector. So as I already said before, this is a scalar quantity. So what you can do is to break this down. Oopsie, what I did. Okay, no, I didn't want to do this. Okay, and I'm making a mess. I want to do this. Erase this thing. Okay. What you can do is to break this down, because I gave you before the expression, the explicit expression of quadratic form, right? You can break this down into scalar terms and then use the linearity of expectation, bring the expectation inside a sum, compute each term, and then write it, see what happens. But we can do it in a more elegant way. So there is something called the trace operator. What is the trace? The trace of a matrix M is simply the sum of its diagonal elements. Okay? Now it turns out that the trace operator has the following property. If I have a product A, B, and C, remember that matrices generally do not commute. So the product A, B, C is different from the product, for example, B, A, C. Okay? But it turns out that when we take the trace of a product, this is invariant to cyclic shifts of the terms. So this is the same as the trace of, if I do a cyclic shift, this will be CAB. Okay? And of course, if I do another cyclic shift, or I shift in the other direction, I would get B, CA. Okay? So now here we have effectively three objects. Or I use a different color. Object number 1, object number 2, object number 3. So this could be A, B, and C. And now you could say, yes, but this is not a trace. Correct. But I said before that the quadratic form is a scalar quantity, and it turns out that the trace of a scalar quantity is the scalar quantity itself, because a scalar quantity is nothing else than a one-by-one matrix that contains only one element, that by definition is also diagonal elements, is the one-one element. So you take the trace, you take the sum of itself and nothing else, so you get this element. Okay, so we can write that this can be written as expectation of trace of our product of vector times matrix times vector. Now I use the cyclic property and I write this as expectation of trace. And then basically I do a cyclic shift, so I put this, then this vector, and then this goes back, and as I have this one. Okay? Right? Now it turns out that trace is a linear operator, and linear operators, and also expectation is a linear operator, and linear operators have the nice property that they commute. So the expectation of a trace is the trace of the expectation. So also the matrix multiplication is a linear operator. So this matrix is a constant. The random variable is also inside here. So we have trace, and then this is expectation commutes here. Okay. And now somebody should tell me, what is this? Well, this is by definition is the covariance matrix of the vector x, because the covariance matrix cov x, which is sigma, is defined as expectation of x minus mu times x minus mu transpose. Mu is the mean. That's the generalization of the concept of variance. Remember that when I multiply a column vector times a row vector, I get, this is called the outer product of two vectors, I get a matrix. So this is a column vector, this is a row vector because it's transposed. So this is a matrix that contains all possible elements of the form xi minus its mean times xj times minus its mean for all possible i's and j's. So when we take expectation, what we have here? Well, we have a matrix that has on the diagonal all the elements for I equal to j, which are exactly the sigma I are exactly the variances of the components xi minus mu I square, and on the off diagonal sigma ij are the so-called covariances of the pairs ij, which are defined as the centralized second moments for all possible pairs. Where you take the variance, you subtract the mean, you multiply them, I and j, take the expectation. Okay, so what we have here, we have that going on, moving on here, we have that our term is trace of sigma to the minus 1 times sigma. Okay? And this is trace of the identity. The identity is a matrix that has all 1 on the diagonal, so this is just the dimension of the vector. Okay, is n. So what we have done here is that this term, we have log e, because the Gaussian distribution has here exponential. This exponential is e to the exponent, is really the natural base of logarithms. So when we take log 2, we get a log e factor there. Okay? So this log e stays, and this thing is simply 1/2 n times log e. So altogether, when we pick all these three terms together, we find this final expression here. Okay, is 1/2 logarithm of 2 pi e to the n times the determinant of the covariance matrix. Okay, and notice that the covariance matrix is generally positive semi-definite, so this determinant is always greater or equal than 0, and in fact, without loss of generality, we can focus only on Gaussian vectors that have a strictly positive covariance matrix, because if I have a Gaussian vector that has a covariance matrix with determinant equal to 0, it means that I can express some of the components as a deterministic function, in fact linear functions of the other components, which means that some of the components are redundant. So I write it here, general fact about Gaussian vectors is that if determinant of the covariance is equal to 0, then I can consider an x. So, sorry, I can write my random vector x as a transformation of some other vector with a smaller dimension n prime, with the n prime less than n, such that this part is simply for example, is simply an invertible matrix of dimension n prime times n prime, and this part is n minus n prime times n prime. It means that you can take the last n minus n prime components of x and write them as linear combinations of the first components of this new vector, which means that essentially at this point the entropy of this vector is, the differential entropy of this vector is the same as the differential entropy of this new vector here, because there is no the remaining components are deterministic function of the others and do not count in a certain sense. So we can restrict to strictly positive determinants for which this differential entropy is well defined. It may be negative because nothing tells you that the argument of this logarithm is greater than 1. So you may have log of some quantity less than 1, and then you get a negative number, but still, this is a finite value, okay, for well-behaved, say, non-degenerate Gaussian random vectors. Okay, so because it's very important in communication theory, and because we do these Gaussian channels because they are good model for communication channels used in practical communications, I want to introduce also the concept of complex Gaussian random vectors, and in particular, a special family of complex Gaussian random vectors that are called proper complex Gaussian random vector, which essentially appear many times in many communication problems. We will see how later on, when we make the bridge between information theoretic models and communication theoretic models. At the moment, you just take it as a definition. So we define a proper complex Gaussian random vector, or also known as complex circularly symmetric Gaussian random vector, indicated with the symbol Cn to remind that it's complex normal and not just normal, with mean vector mu and covariance matrix sigma, as a random vector that is written as the sum of a Gaussian random vector xr, the real part, plus j, another Gaussian random vector xi, the imaginary part, and such that the xr, the real part, is normal with mean real part of the complex mean value and covariance 1/2 of the complex covariance matrix, and on the imaginary part has essentially the same statistics by taking here the mean is the imaginary part of the mean and the covariance is the same, is 1/2 sigma, and in addition the real and imaginary part are statistically independent. So they are like two independent random vectors. So it turns out that what is the joint distribution of this complex random vector? Well, the joint distribution of a complex random vector is always given as the joint distribution of the imaginary part and the real part and the imaginary part. So in this case, because they are statistically independent, what we can do is to write, complex. So the joint distribution of p x r, let's say xr, times p xi xi. The joint distribution is just the product because they are statistically independent. So the joint PDF is the product of the PDFs. And so we use the formula we have seen before. So in this case, we have 1 over 2 pi to the n½ times the determinant of sigma. So the determinant of sigma, we have 1/2 sigma to the 1/2, and then exponential of minus, here we have 1/2, and then xr minus the real part of the mean, and then we have, so when I take the inverse of 1/2 sigma, I get 2 sigma to the -1, so the 2 and the 1/2 simplify, so this 1/2 disappeared, so I have sigma to the -1, and then I have xr minus real part of mu, no? And then times, and then I have the other term, 2 pi and ½ 1/2 sigma determinant to the 1/2, and then I have xi minus imaginary part of mu transpose, and then This is imaginary part. Okay. Now it turns out that if I collect things in a different way, so the two exponentials go together because it's the product of exponents, is the exponent of the sum. So these two go together. These two factors we have here, that the 1/2 in front of sigma, when you take the determinant, you get 1/2 to the n, but then there is this factor here. So we have 1/2 to the n-half here, that's simplified with the 2 to the n-half here, and the same thing on the other side. So we have this pi to the n-half times pi to the n-half makes pi to the n. So at the end here we have pi to the n times determinant of sigma, because you have a square root of determinant of sigma here, square root of determinant of sigma there, you get just determinant of sigma. And then if you look at these two and you put them together, you find that you can write these as simply the complex vector Hermitian transpose sigma to the -1 times the complex vector. Okay. So in general, the quadratic form with complex random variables is written as A Hermitian transpose a positive semi-definite Hermitian matrix. So what is Hermitian transpose? Hermitian transpose, it means that if you have a vector Hermitian transpose, this is a vector that contains A1 conjugate, A2 conjugate, and conjugate. So it's the transpose of the vector, and then you do conjugation of each element. Okay? This is called Hermitian transpose. And an Hermitian symmetric matrix is a matrix. When you take the Hermitian transpose, you get the matrix, the same matrix. A symmetric matrix is a matrix for which you take the transpose and you get the same. Invariant by transposition. Hermitian symmetric is invariant by Hermitian transposition. Okay. So, and a property of covariance matrices is that they are symmetric for real vectors and Hermitian symmetric for complex vectors. Okay. So, in other words, this says that we can compactly write down the PDF of the complex Gaussian random vector in this form without having to separate real and imaginary part. Okay? And so we write simply here, and the general form for a Gaussian random vector PDF with this special condition of being circularly symmetric. So it means that the two real part and imaginary part have the same covariance matrix and they are statistically independent. In this special case, the complex vector admits this form, and this is formally a function of a complex random vector, sorry, a complex vector. So you would say, okay, exponential of a complex variable is complex, but it turns out that a property of Hermitian quadratic forms is that this value here is always real positive. So, or say real non-negative. So this exponential is always exponential minus a real quantity, which is real non-negative. So this is a well-defined function. This is a real valued function. Okay, although the argument is complex. And it turns out that if you repeat the same operation as before, you find that the differential entropy of a complex circular symmetric random vector is a logarithm of pi e to the n times the determinant of the covariance matrix. So when you compare these and what we had before, we see that the difference between real case and complex case is that in the real case we have a 1/2 here and we have a 2 here. Okay, in a complex case, this factor of 2 disappear. Okay, good. So those were just examples. Now we have formulas for of course, you can find explicit formula for differential entropies for other random variables, Laplacian random variables, exponential random variables, all sorts of continuous random variables for which you can, either in closed form or just left indicated as an integral, you can have a differential entropy. Now, extending, oopsie, what happened here? I touched the wrong button. Okay. No. Okay, good. If this, I touch the wrong button, this explodes. So extending the concept that we have developed for entropy, we have similarly for two jointly distributed random vectors x and y, we can define the conditional differential entropy of x given y, which is exactly the same definition. It's minus the expectation of the logarithm of the conditional density. Okay. We can define the divergence between two distributions. If we have two distributions P and Q defined, so there are the PDFs, the probability density functions defined on the real line, or more in general on the real d-dimensional space, the Kullback-Leibler divergence or information divergence or simply divergence between these two distributions is defined as the integral of P times log of the ratio P over Q. Is completely symmetric with what's seen for discrete random variable. Simply you replace the PMF with the PDFs. Now, one thing that is interesting is that this divergence is always greater or equal than 0. So this property of non-negativity of divergence remains also for continuous random variables. Okay, so while the differential entropy is not really an information measure, the divergence is in fact an information measure and has this non-negativity property. And in particular, you can show that this divergence is also finite whenever the support of P is included in the support of Q. So they may have the same support, for example, the whole real line, but, well, technically speaking, in the language of measure theory, we say that P must be absolutely continuous with respect to Q, but, okay, let's say, intuitively, we don't want any x for which the numerator here is non-zero and the denominator is 0. If this happens, of course not for a single point, but it happens for a point, say let's say a set of probability measure non-zero with respect to the measure P, then these things go to infinity and explodes. So, and then we can define the mutual information between two random variables x and y with joint density pxy, simply as the divergence between the joint density and the product of the marginal densities. So it's an integral with respect to pxy of logarithm of the ratio between the joint density and the product of the marginals. Again, since this is divergence, the mutual information is always greater or equal than 0, and it turns out to be exactly 0 if and only if the two random variables are statistically independent, for which the joint density coincide with the product of marginals, and therefore this ratio is always 1, and log of 1 is 0, and therefore the mutual information is 0. Okay? So while the differential entropy is maybe negative, the mutual information, even for continuous random variables, is always a non-negative quantity. And the relation between mutual information written in various forms and differential entropy is exactly symmetric with respect to what we have already seen for discrete random variables. Simply you use differential entropy instead of entropy. And we also have this result for which the mutual information can be written as a conditional divergence and can also be written as a difference of divergences, where we can introduce here an arbitrary distribution, as long as these divergences are well defined, for which all these terms are finite. And this q sub y is not p sub y. Q sub y is an arbitrary PDF for the variable y. Good. So this follows exactly the same way as whatever we have proved in the first week. You simply replace summations with integrals, and you find all this relationship. An interesting point is that because the mutual information is non-negative, and because we can write the mutual information as the difference between differential entropy and conditional differential entropy, then if this difference is always greater than 0, it means that this quantity, the conditional differential entropy, is always smaller than the unconditional differential entropy, which means that in general, also for differential entropy, conditioning reduces differential entropy. Then, exactly as for discrete random variables, we have chain rules for the differential entropy, for which, if we neglect this conditioning, we get an upper bound, which is the independence upper bound, for which the joint differential entropy is always upper bounded by the sum of the marginal differential entropies of the components. In passing, using this bound, this independence bound applied to Gaussian random variables, we can prove, for example, using information theoretic tools, an inequality which is an inequality for matrices, known in other ways from matrix theory, which is called the Hadamard inequality, that says that the determinant of a matrix is always less or equal than the product, the determinant of a positive definite symmetric matrix is always less or equal than the product of its diagonal elements. So how do we see this? Well, we apply this independence bound, to the Gaussian differential entropy. So we know that the joint differential entropy of a Gaussian random vector with the covariance matrix sigma is given by this formula, and the components, a property of Gaussian random vectors is that each component is individually Gaussian, and in fact the variance of the ith component is simply the II elements of the covariance matrix, as I said before. So the marginal differential entropies of the components are simply the same formula applied to single variables with here, instead of the determinant of the covariance, is just the variance of that component. Now, if we use the fact that the sum of logarithms is equal to the logarithm of the product, and then we use this inequality, the monotonicity of the logarithm implies that the determinant of a positive definite symmetric matrix sigma is always less or equal than the product of its diagonal elements. This is known as Hadamard inequality in matrix theory. Of course, we also have the chain rule for mutual information. So when we want the mutual information between one variable and a vector of n component, we can develop the mutual information with respect to the components of this vector in the following well-known form that we have already seen many times in many exercises for the case of discrete random variable. Everything holds verbatim here. Okay? At this point, I want to conclude this overview of differential entropy and continuous random variable by introducing an important result. The result that given by this theorem differential entropy maximizer. So let xn be a random vector with mean 0 and given covariance matrix. So I don't know what the distribution of x. I'm not saying x is Gaussian, but I fix its covariance matrix. It turns out that its differential entropy is always upper bounded by the Gaussian differential entropy with the same covariance. And for complex proper random vectors is the same thing. Given a complex vector with a covariance matrix sigma, then its differential entropy is always less or equal than the Gaussian differential entropy for the same sigma, which means that the Gaussian random vectors maximize the differential entropy over all random vectors with the same covariance. That's a very important property that will be used to prove the capacity of the Gaussian noise channel. So how do we prove this? The proof is in fact quite simple. It's a few lines. So let G denote the Gaussian PDF with mean 0 and matrix and covariance matrix sigma, and let in fact P sub xn be the original PDF of this generic random vector. All we know is that it has the same covariance matrix that has mean 0, but the distribution can be non-Gaussian. So we use the non-negativity of divergence, and we use the fact that a Gaussian distribution is defined over the whole n-dimensional space. So it's never 0 because it's exponential. So for sure this divergence is well defined because the domain of G is the whole space. So we use the definition. Well, we use the fact that the divergence is not negative, so 0 less or equal than divergence. We write the divergence in its explicit form. Then we break the terms, right? So if we take this part, so we write the log of the ratio as log of px minus log of g, okay? And integral of px log px is minus the differential entropy of x. And then we have minus integral of px log g. But log g is a Gaussian distribution. So log g, we have already computed what is the logarithm of a Gaussian density. The logarithm of a Gaussian density, if you remember, was, where was it? I don't remember. Oh, it was before. Okay, it was here. Yes, it's here. You see log of a Gaussian distribution. So now our Gaussian distribution is g of x in our see later, say theorem 20. So what is this? Well, we know what it is. It's a bunch of constants, and then there is a quadratic form. And we know that this quadratic form, when we compute it, well, actually depends only on the second order statistics, only on the covariance of the vector x. It doesn't depend on specifically on the fact that x is Gaussian. At the end, is a quadratic form. It depends only on the covariance through this trick, right? Because at the end we get expectation of this thing, and this is just the covariance of the vector. So what we can do here, we use the following trick. Since, what is our proof here? Since this is a quadratic in x, then the result of this integral is the same for all the distributions with the same covariance, because only the second moment of the result will count. So we can replace P with G, because they have the same covariance. But now, written in this way, this becomes the difference of minus the differential entropy of x plus the differential entropy of the Gaussian distribution. So we conclude that the 0 is less than minus h plus this, or in other words, that this term is bigger than this term. Okay, so this proves the result. You do the same thing for the complex case, and you get exactly the same. You get the second statement there. Okay, very good. So let me just mention one corollary of this result, which is this. Actually, no, it's already pretty long. I'm going to stop here because I want to talk a little bit about estimation error and mean square error, and it takes me a little bit of time. And I think it is also something useful for you because maybe it's something that you're not completely, perfectly confident with. And this is a concept that we will work on later also, and I want a little bit of time to introduce it. So I'm going to stop here and then start from here in the next part.